My name is Jed Hale, and I am a lead cybersecurity researcher at Idaho National Laboratory. Sage Havens is also a cybersecurity researcher at INL, and she was my co-author on this paper and my co-investigator on the research. The work we're talking about today was research done during the Firmware Indicator Translation Project, also known as the FIT project. This work was funded by the Department of Energy CSER CEDS program, which focuses on the cybersecurity of energy systems. The goal of this big project was to provide tools to help defend embedded systems, particularly systems that are frequently found in energy delivery systems such as relays, smart meters, all those kinds of things. Some of the objectives we had was to create a process where we could analyze firmware, have that be a repeatable process that could be automated as much as possible. Another goal was to take the relative wealth of information in terms of IT threats or enterprise threats and figure out what of those indicators and other threat information that's available in enterprise could be applied to energy systems. We also worked on lessons to help understand better when and what sort of binary tools, code translation, and so on can be used and will provide value. We also worked on building a library of firmware references that we can use for other purposes. And a big one also was this ability to identify the software components that are a part of firmware. When you look at a firmware image, it's an entire operating system, if you will. And as such, it's composed of many pieces of software. Some of those may have been written by the vendor. Some of those may have been pulled from commercial or open source libraries. When we think about these systems, there's a lot of layers. We've got the CPU, instruction set architectures, there's the microcode that helps run the CPU, there's some sort of BIOS that runs the entire system at a hardware level, there's an embedded operating system, there's interfaces to other devices such as radios or other peripheral devices. And then, of course, we have the OEM who builds and sells machines. Computing systems. There's third-party integrators that might take a variety of various OEM hardware and software and integrate it into a solution. There's the asset owners who buy these systems from the OEM and from third-party integrators. And then finally, there is maintenance, which is what is done to these systems after they enter production. This could be patching, upgrades, configuration changes, and so on. One of the things we've learned over the years is that there are vulnerabilities at every layer. There's stuff that everyone's familiar with, for instance, Spectre, Meltdown. These are things that targeted very low-level features of the hardware. There was the Lenovo backdoor that was fairly infamous, where there was backdoors in the firmware of certain laptops. Of course, there's an untold number of vulnerabilities at the OS layer, at the software layer, chipset interfaces. There are known attacks against various daughter cards or peripheral devices. There have been instances where the OEM was directly attacked. Maybe their build system was attacked. Maybe some other process of the actual manufacturing development of these devices was attacked. Likewise with integrators, third-party integrators, people using the access that the integrators might have, not just to their customers, but to the OEM, and using that as an opportunity to expand the attack surface, misconfigurations, so on. And then, of course, there have also been lots of attacks against the distribution systems that distribute patches, software updates, and so on. So what we'll be talking about today is something we call @DISCO, which is an acronym for Annotated and Translated Disassembled Code. We developed @DISCO for the purpose of having a tool set to do binary analysis in a consistent way that's automatable and shareable. One of the big challenges that we face as reverse engineers is the currently available tooling that is commonly used is not consistent, and different people who work in this field might use different tool sets, and not a lot of work has been done in terms of being able to move data between the various tools, being able to share data across the team, being able to have some relatively easy way to take all of the results and findings of your analysis and give it to someone else so they can reproduce it or so they can do further analysis and so on. And finally, none of this scales. It's very, very dependent on all the humans in the loop. So @DISCO, we work to rectify a lot of that. We also use @DISCO to create corpora for large-scale binary analysis and machine learning. @DISCO sits on top of a graph database. In particular, we've been using OrientDB. It provides us the ability to run graph traversal queries that might return a control flow graph or an flow of execution graph or a data flow graph. And we can use these types of capabilities then to build systems that can identify all of these software components that might be a part of a firmware image. This is also useful for looking at change detection, where we can detect when changes have been made to a piece of software, which is very, very useful in forensics and potentially useful in other aspects of system maintenance. All of these things, of course, contribute to a better understanding of these complex systems and how the components work, how the components interact, and what the attack surface looks like. And the better we understand the entire system and all of its components and all of the interactions and the attack surface of each, that means there's less unknowns. And the less unknowns we have, the easier it is to build resilient systems. As a motivating example here, I'm going to talk about a ubiquitous library, or a commonly found library that was in use in BusyBox for years. Many of you are probably familiar with BusyBox. It is an operating system that's often used in end-user-oriented embedded systems. It's free, it's open source, it's basically Linux. One of the things that BusyBox uses is the OpenNTP daemon, which is a network time protocol daemon. In 2009, there was a vulnerability discovered in OpenNTP, and it was patched shortly after the vulnerability was discovered. We went and looked at BusyBox to determine when they patched, included the updated library in the BusyBox system builds. And we found that it was not until 2016 that the OpenNTP version used in BusyBox was upgraded to one that had been patched for this vulnerability. We also used BusyBox to build a test corpora, where, a lot like Brian talked about in the previous presentation, we took all these different versions of BusyBox over this period of time. We built them, we cross-compiled them on 14 different architectures using 2 different compilers and 4 different sets of optimization flags, yielding us approximately 2,000 different compiled copies of BusyBox, 2,000 BusyBox binaries. So here's how the analysis phase of @DISCO basically works. It takes the binaries that we give it and it disassembles them and does a certain amount of static analysis, where static analysis is analysis that is done to the binary code or the assembler of the analyzed binaries without actually executing it, without doing any sort of binary dynamic runs of it, without anything, just by purely analyzing the assembler itself. Some of the important outcomes of this process is finding and identifying all the functions that are present in the software and identifying each. Where does it start? How long is it? What are all the instructions that belong to this each function, and so on. Next, the function is broken down into what we call code blocks. And a block of code is all the code that occurs between a fork. If there's an if statement or a goto or any kind of a jump, anything like that where the path of execution or the path of control changes, all that code's a block. And for each block, we generate a feature set that can serve as a representation or a fingerprint of each block. We put all of this information into OrientDB to capture the analysis. If we look at this chart here, this diagram on the bottom, the orange node here represents a library. The two blue nodes represent two functions that are part of that library. And if we follow the has block edge, we see these two yellow nodes, which would be blocks. In this case, each of these functions only have one block. Number 164 on the bottom here is interesting because we see it calls function number 217. And also each of these two blocks has a single feature set, has one feature because we're building a feature set per block. Going a little deeper into this, since we're using the open source Anger binary analysis toolkit for this research, one of the things that Anger uses is an intermediate language representation known as VEX. And VEX was designed to be a platform neutral assembly language almost. So it is able to represent the logic of any platform's assembly language. If we look here on the bottom, we see on the left x86 assembly for a Hello World program. And you can see the various x86 calls that are made. And then here in the middle box, we have the VEX intermediate representation of that same assembler. So the thing we did here to build a feature set was we decided to count how many VEX instructions are used per block. In other words, if we look here on the right at the instruction counts, you can see that IMARC was 6, and there's 1 ABI hint, 9 read temp, 2 write temp, 5 write temp, 2 stores. And by taking these and putting them all together, we have what we could call a function representation or a feature vector for it. And to represent an entire function, we just simply take the block vectors, the block representations, and sum them up, and that then becomes a function representation. Now, this is in a lot of ways similar to the bag of words approach that's used in natural language processing, and these could also be considered, these could be regarded as histograms as well. So what we want to do with this is identify ubiquitous libraries. We want to be able to take a piece of compiled software and be able to rapidly determine, is it using OpenNTPD? Is it using libxml? Is it using libpng? What's in there? And even also, we want to be able to identify the version of each. So we began working on ways to do this using these function representations we have, and we used the at-disco toolset to build this machine learning corpora that would be appropriate for supervised machine learning approaches. One of the things we needed to do was have a labeled training set. So we took a large number of commonly used software libraries, like the ones I've been talking about, OpenNTP, libc, and so on. And we ran them through @disco. We compiled them using our compiler architecture, our compiler infrastructure, analyzed all the different outcomes of that compiling, labeled them all, and put them all into the @disco database. When we also did that with firmware, where we happened to have good labeling information about which functions were which, in other words, firmware that wasn't stripped, and other compiled software that we had available. Did this whole process of analyzing and vectorizing, putting it into a graph database. The first thing we did was we just tried to take the unknown binaries where we did not know what the functions were, and directly compare those function vectors against the ones that we had learned or found in the various software libraries in our training set, with the idea that once we could match those functions, then we could go back and cross-reference those to their original library just by querying the database. With the next thought being, at that point, we could go and query a vulnerability database to determine if the libraries we found contained any known vulnerabilities. We rapidly found out that just simple matching of these vectors was not enough to give us any accuracy. In this diagram here in the bottom, we can see two functions that are, from the name, are probably pretty similar, but they're not exactly the same. Register printf specifier versus register printf function. These two multicolored blocks you see here are just a heat map that represents these function vectors that we've been talking about. So the closer to red the color is, the higher the count is for that particular vex instruction. And the dark blue in these, the darkest color, are where the count was 0. But we can see just by a simple glance at these that these two appear to have the same fingerprint, which is problematic, right? So we decided to go ahead and try some all your introductory type of machine learning approaches to this to see where it could get us. We looked at using K, nearest neighbors, and looking at the clustering. And this, in the chart on the bottom left, we can see a KNN clustering here, and where each of the various functions that we had in the test set are represented by a different color. And so you can see here that a lot of stuff of the same color is clustering together. We also tried using support vector machines as a classifier. In this chart on the bottom right, you can see a plot of the support vector machine classifier with the various ranges of values that would be chunked into the different classifications. And it turns out that this all worked fairly well. We also did some work with slightly more advanced multi-layer neural networks, CNNs, or convolutional neural networks. And we wound up finding a machine learning system which could not only identify which libraries are present in a firmware image, but it could also identify and label each individual function to a high degree of accuracy. And due to the way this whole @disco toolset works, it can be an automated process. In other words, you point it at the binaries, it goes through this whole process we've been talking about. In the end, you have identification of functions and libraries. This is incredibly valuable to anyone who's doing vulnerability research or anybody who needs to understand the very specific software details. Here's an overview of a few of our results. In the top left here, in this table, we have a number of classifiers that we pulled straight out of scikit-learn, along with F1 scores. And these results are against our reserved. We held back 20% of the training data as test data. This test data was never used in training the models, just strictly for post-training accuracy testing. And we can see that the other important thing to note here is each of these, we didn't do any hyperparameter optimization of any of these algorithms. We just ran them straight through with their default settings, which, as a lot of you probably know, isn't optimal, but we wanted to just see how that worked out for us. And we can see we got pretty consistent results mostly. K-neighbor classifier 94%, decision trees, random forest, the neural net module out of scikit-learn. AdaBoost for some reason was particularly bad. Naive Bayes did well. Then the next thing we did was we tested against a couple of basic neural networks that we built, which are, their general overview is shown here, where in the case of the multi-layer perceptron or multi-layer neural network, it was 4 linear layers basically that were interconnected, and in the case of the CNN, it was 2 convolutional networks connected by 2 linear networks. The box on the lower left shows our results for some of this. So this example just shows a few specific function labels, function names, and then the numbers going across show the precision, recall, F1, and support scores. So for instance, for GI FX stat 64, we can see that of the 14 cases here in the test set, it was perfect. Likewise with IO adjust column, and then we get to IL default excess get in. We can see here the precision was 0.95, F1 0.97, and the reason that when we went back and analyzed these cases, like with this one and IO file fopen here on the bottom, when we went back and analyzed them, these were cases where, due to the simplicity of this feature representation, we had colliding function representations. In other words, the instruction counts for IO file fopen collided with some other functions that we also had in the database, resulting in, of course, a loss of precision and accuracy. So what can we do? What can we do? So that's the next question. To summarize where we've been so far, what @Disco gives us is an automated set of tools to improve our understanding of firmware and the software components that are included in firmware. This includes a way to automatically compile, analyze compiled software and firmware, load it all into a graph database where all of your analysis is stored for future use. It gives us a tool set for building and maintaining all kinds of different corpora for machine learning. And we have used @Disco not just for the machine learning we're talking about here, but for other machine learning tasks. It also gives us an automatable and efficient way to enumerate all of the software components that are present in compiled software or firmware, which is an extremely important task when it comes to understanding attack surface and understanding the vulnerability, the risk associated with deploying different devices. It gives us the ability to basically use this enumeration of software components and query vulnerability databases or other threat information sources to discover what vulnerabilities are out there, what advisories are out there, and do they apply to the particular version of what we have or not. The other big thing, this needs to be able to be done realistically as fast as possible for as many systems as possible. Otherwise, it's just another research curiosity. And that was a big goal of ours, was to try and build a system where that kind of scalability could happen. And it wasn't limited by having a lot of reverse engineers manually trying to do this work without any assistance. A couple other big takeaways that we have from this is that this kind of advanced knowledge of the state of the software and how it's built and what components form it are an advantage to a lot of resilience technologies. Resilience can be improved by improved understanding of exactly what it is you're trying to achieve resilience for. This could also be used as a software component in other kinds of new resilience research, perhaps where new research in resilience actually leverages these types of automated software analytics as an actual part of the research itself. So going forward, there's a lot of things we learned in this work. And a few of the big ones are, we realized we needed to be able to move away from strict supervised machine learning. One of the big reasons for that is, especially on some of the more closed platforms where we're never going to get access to any kind of source code, we're never going to even get access to debug files or anything that we could use to create labeled training sets. That's a problem. So we need a way of being able to do this and reach some form of accuracy without having a label for everything. And we need to be able to get away from classifiers, because classifiers really only work for classifying the stuff they know about. If you have something that's outside of your classifier's domain, that becomes an issue. One of the ways we've been working to address these challenges is moving to transformer-based machine learning models that are capable of doing cross-architecture analysis. One of the other things we found during this research was that even though VEX itself is platform neutral, if you take the same code and you compile it on ARM and you compile it on Intel x86, and then you build these function vectors like we've been talking about, the counts will look different just because the way ARM does things versus the way Intel does things, they both came from the same source code, but those counts are a bit off. And sure, you can work around that in a supervised model and train a model that can account for those differences. But again, we go back to the fact that that's always going to be limited. The thing we realized very quickly was this kind of feature representation, an engineered feature representation, isn't going to be discerning enough or detailed enough. And we spent some time trying various other engineered feature sets, but ultimately always kind of came back to the same problem. So we worked on developing a learned feature representation where a machine learning model itself develops the features for our function representations. This also gave us the ability to use cosine distance as a similarity check, spectral similarity, meaning we don't have to rely on a classifier. Once we get the function representation, we can just go and query our database of all of our other function representations for the one that has the best cosine similarity, and that's going to be our closest match. And this is one of these things that really opens the door for unsupervised machine learning for us. We also worked on improving our static binary analysis capabilities so that, especially in those cases where we may not have complete labeling for everything in a binary, how can we do static analysis to better improve our odds of correctly identifying what's what? We're also moving forward with adding symbolic execution and dynamic analysis techniques to the systems, which can give us the ability to learn and resolve some things that just aren't going to be possible through static analysis alone. We're also working on ways of having machine learning systems help improve the disassembly process itself. For instance, Weebin is one example of that. One of the big challenges when you're disassembling an unknown piece of software is, where's the code in this thing? Where do we actually point our disassembler to do the disassembly? what's the base address? There's all these little bits of trivia you need to know to get good disassembly. And if you don't have good platform documentation, it's very difficult to do. There's opportunities for machine learning there to improve that. And we've been hints at some of those capabilities that we could develop. We also have new research focusing on applying these types of techniques to malware and other types of hostile software. And we also have research that is focusing on using these same types of techniques for validation. And this isn't strict formal validation in the sense of using theorem provers to do the validation, but more of something that maybe gets us close to that without having to go down the path of doing a full formal validation. And that's what I have for today. Any questions?
Thank you, Jed. That was very interesting. We do have a question. We may have several in here, but the first one we have is from Derek Remenius. If you have access to malware binaries, could you generate a graph representation of the malware and perform a matching the binary to see if the binary contained the malware? Similar to that, similar to what you did with the libraries, just with malware instead.
Yeah, that is definitely the purpose of some of our current research, applying these types of approaches to malware and figuring out how can we identify malware, understand what the malware does, where did the malware come from, what might the malware target, right? All these things that we need to know as rapidly as possible when an attack is happening.
I had a question of my own too for you. I was wondering, can you think of a case where you would have to use reinforcement learning when you're going through this?
It's a topic I've thought about quite a lot. In particular, where we were talking about machine learning and using machine learning to improve disassembly. I have some schemes in mind there where it might be a reinforcement learning type of scenario where basically maybe, I guess so, just a real high level, okay, you attempt a disassembly and then you pass that to some sort of your scoring oracle that then basically can grade the quality of that disassembly and kick a score back to the reinforcement learning algorithm. That would be one example of that kind of thing. So yes, reinforcement learning is definitely something we'll be researching more in the future.
Okay. Are there any other questions? Doesn't look like it.
Yeah, there's a question.
Which one? I'm not seeing that. I just saw
Is Disco available to the public? Travis Gilbert asked.
Oh.
So we are working with our customer, the Department of Energy, on defining the exact constraints we'll be under. Yes, we intend to make as much of this possible available to the public, and it's possible just due to various restrictions on this kind of research. We may only be allowed to offer it to U.S. citizens, but we're working on it, and you know, when we get to that point, we'll certainly make a public announcement about its availability.
Great. Thank you, Jeff, for that talk. That was very enjoyable.